Welcome to Oxidation and Reduction. Here's a little demo. Solution of zinc nitrate, a solution of copper 2 nitrate. Piece of copper, piece of zinc. Take the copper, put it into the zinc nitrate, you look at it, nothing happens. You put it into the copper 2 nitrate. That's a pretty clean piece of copper. Take a piece of zinc, put it into the zinc nitrate solution. There's no reaction. Put it into the copper 2 nitrate. Oh, that doesn't take very long at all, does it? You look at that, and there's a reaction where the zinc metal is breaking down into zinc ions, and copper ions are forming copper metal on here. They're pretty dark now, but that's solid copper forming. So many of the reactions that take place on this planet involve the exchange of electrons from one substance to another. Even the majority of the reactions that we had in the last unit, certainly all the combustion reactions that we did in the energetics unit, were all exchanges of electrons. So even though explosions might happen and a vigorous reaction occurs, that's usually the result of exchanges of electrons between elements. Now, exchanges of electrons, this gives us the redox unit that we're doing right now, or electrochemistry, because that exchange of electrons causes a current to be able to be formed, because electrons are electricity. So this is what we're studying here. And the redox term means reduction, oxidation. So the copper-zinc demonstration that you just saw, I'll explain right now in terms of the equations behind it and what was happening underneath the surface, so to speak. Okay, so what we saw was that the zinc metal was turning into zinc ions and breaking down, while the copper in solution, the Cu2 positive ions in solution, were actually forming solid copper. There were two things that were going on there. The zinc is breaking down into zinc ions and giving up 2 electrons. So you see how that's balanced. 2 positives and 2 negatives, 0 total on this side, 0 here. And that's called a half reaction. 2 half reactions together make up a whole reaction. So the other part of that was that the copper ions were gaining those 2 electrons right there to form solid copper. So these 2 reactions together make a net equation. Okay, now there are some terms, some definitions that are absolutely vital. You've got to understand them. You have to memorize them. You really do, because a lot of the tests that teachers do is just testing you on the terminology here. So, when a substance goes from being a metal or a certain chemical and breaks down to form electrons, that's called oxidation. Oxidation means losing electrons. And losing electrons means that the substance has the electrons written on the right-hand side of the equation. Zinc is being oxidized. It's losing 2 electrons. Now, the copper ions here are gaining 2 electrons. So the copper ion is undergoing reduction. Reduction means gaining electrons. Now, I know that sounds kooky because you say, reducing means gaining. That doesn't make sense. But then again, chemistry doesn't make sense, so that makes perfectly good sense. But what it really means is this. See that charge of 2 positive there? It's turning into a charge of 0 for copper. 2 positive is going down. It's being reduced to 0, and therefore gaining electrons reduces a charge. So that's why it's called reduction. Okay, so we've got oxidation, reduction, and we can't add 2 equations together that both are reduction or both oxidation. This unit isn't red-red and it's not ox-ox. It's redox, reduction and oxidation. So one's always losing, the other one's always gaining. That makes sense. Now, if this loses 2 electrons and this gains 2 electrons, the ratio of reaction between them is like 1 to 1 here. And so we take this reaction and this reaction, add them together. When you add them together, you do realize, of course, that the electrons cancel out. So you get this and this reacts to form this, and that is the net ionic equation for this reaction. You know, you can get a list of substances and are asked to then determine out of that list of substances what the oxidizing and reducing agent is, and you need a chart to be able to do that. And so your teacher's going to give you an oxidation reduction chart, and they're generally written this way, with the things that like to gain electrons the most at the top left-hand corner, and they're all written as reduction reactions with the electrons on the left-hand side, and then the things that like to lose electrons the most are found on the right-hand side, closer to the bottom actually. So, on these charts, you have to be able to determine who the strongest oxidizing agent and reducing agents are. I'll tell you what that means. If this substance is undergoing oxidation, that means that it was influenced to lose electrons by the copper ions, who were the agent of oxidation. So now get this. Anything that's undergoing reduction itself, it is a strong oxidizing agent, or an oxidizing agent. An oxidizing agent undergoes reduction. Reduction means you are gaining electrons. Gaining electrons means they're written on the left-hand side. You've got to make sure that that gets memorized. So, this must be the thing that influences this to undergo oxidation, right? Or, sorry, reduction. Yeah, that's right. This is undergoing reduction. This tells this to undergo reduction because it really gives electrons to it. And so that means that this chemical right here is the strong reducing agent. Reducing agents undergo oxidation themselves. And that means that you write the electrons on the right-hand side. So, oxidizing agents undergo reduction. Reduction means gaining electrons. And then, for these guys here, a reducing agent means you're undergoing oxidation, which means you are losing electrons and you write them on the right. Okay, now let's do a question that you might see in class. So in approaching a question like this one, the first thing you want to do is take any kind of ionic compound, and break it up into ions in solution, and then check this redox chart that you have, reduction potentials chart, to find the highest substance on the left side and react it with the lowest substance on the right. If they're all written as reduction reactions and that the highest voltages you'll see on the far right hand side are listed from highest positive value to lowest negative. Okay, now when you do that, here's what you get for this one. A list of chemicals first. I like to start off with a list that says I've got lead solid and silver and nitrate ions, that's silver nitrate, swimming around in solution, and water. Water's a reducing and oxidizing agent on the chart, on both sides. But the highest one on the left is the silver ion and the lowest on the right is the lead ion. So silver's up here, lead's down here, and what we've got is a redox reaction that can occur. Now, all we do is this. Find the SOA, which is the one on the left-hand side, and all you do is you write the half reaction out from left to right, exactly the way it says on the chart. Just write it out. But the one that's the SRA on the right side, SRA, I know it's reducing agent, but it stands for the right. You've got to take that reaction and realize that if you copied it out from left to right as well, you'd have two reduction reactions. So you reverse it. The SRA on the right side gets reversed. And you take that reaction, the half reaction that you see in the book, and reverse it. So you make it oxidation, and then you can add it to the reduction reaction. When you do that, you have to make sure that the electrons cancel. And in order to make sure of that, you've got to see that there's a ratio here of 2 electrons being lost, but I'll only gain 1. So we've got to run through this reaction twice. This half reaction gets multiplied by 2, then added to this one, so the electrons can cancel. You can't have electrons left over in the net equation. They have to cancel. So you get 2Ag positive plus lead, and that's going to make lead ions and silver. That's a solid, that's AQ, that's AQ, and that is AQ, and that's not AQ, that's a solid. Sorry. Okay, now, here's the thing. That's the net reaction. And you can find what they call the voltage for that reaction, or the E naught. The E just stands for the voltage, and naught means standard conditions of 25 degrees Celsius and 1 atmosphere of pressure. The E value in the book for this reaction is 0.80 volts. The E value for this reaction is negative 1.23, but if you reverse the equation, you reverse the sign. And so it becomes positive 0.13 volts. All you do to get the E naught of the net equation is to add those two voltages together. Add the SOA's voltage to the reverse of the SRA and you get 0.93 volts. By the way, you know what that means? That means that this reaction does take place because it produces electricity. The reverse of this reaction would be a negative 0.93 and it wouldn't actually occur naturally. When a reaction occurs and it's got a positive voltage, we say it's spontaneous. And that will mean on this chart that it'll be left over right. Oxidizing agent over reducing agent. But if it's right over left, in terms of the strongest oxidizing and reducing agent, you'll get a reaction that doesn't occur naturally and normally, and that's going to have a negative voltage, and it's called non-spontaneous. Now, you may say, okay, chem guy, that oxidation number stuff, I understand that, I get it, but is there another way to balance this reaction successfully without using those numbers and stuff? Okay, there is. Now, that doesn't mean that this method, which sometimes I do prefer, it doesn't mean it takes the place of understanding oxidation numbers, because you may be just asked in a question, hey, what substance here in this reaction, it's always in the reactant side, what's undergoing oxidation? By using oxidation numbers, you can easily determine something that's undergoing oxidation or reduction. But this is called the half reaction method, where you break this equation down into two half reactions and then you build your own half reactions. And watch how this is done. The rules are, as we go through, I'll explain. What we're going to do is we're going to take two principal chemicals in here and break them down into half reactions. Well, look at this Mn. We know that MnO4 negative here has to somehow turn into Mn2 positive. So we write MnO4 negative turns into Mn2 positive. Hydrogen and oxygen are not necessarily the principals in any reaction. It's the other elements that look kind of different from reaction to reaction that we actually split up. Fe has to turn from 2 positive to 3 positive. With that, we've got two half reactions now we're going to add together to get this net reaction. We are. But it doesn't look like, well, where's this going to go? Is this going to go in this one? Is this going to go in this one? Now, it's okay. You make your own. Watch how you do that. When you need oxygen, you add water. When you need hydrogen, you add H positive. And then, in order to balance the charges, you add electrons. So follow those three rules and everything works out great. Here's how it goes. I have a half reaction here that doesn't have oxygens on this side. When you need oxygen, add water. Oh yeah, but wait a minute, there's 4 O's here. We're going to put 4 H2O's in front, and now you've got the oxygens balanced. Oh yeah, okay, well, now I've got hydrogens on this side, but none over here. When you need hydrogen, add H positive. Okay, add H positive. Oh yeah, get it? Okay. Now, you've got to balance with charges. 1 negative here. Uh-oh, but there isn't 1 negative here. There's 8 H's. Whoops! You got to put an 8 there. You got to be careful. You got to go through this and make sure that you catch yourself, like I just did, in terms of the number of atoms you have all the time. Now, that's 8 positives and 1 negative is 7 positives on the reactant side, but only 2 positives here on the product side. So what do? You actually have to add negatives. To which side? To this side over here. And if you add 5 negatives, 6 negatives, 8 positives makes 2 positive total on this side, 2 positive total on this side. So just be careful, do that, and you'll get it. 2 positives here, 3 positives here. You don't have to add hydrogens or oxygens. What do? Well, we add 1 electron here. Hey! We're ready to add them together. But look at, just like we discovered with the oxidation number balancing of this, you've got 1 electron here and 5 here. And so you take this whole half reaction and you multiply it by 5, so you can have 5 electrons here, canceling 5 there. Electrons have to cancel out for the net reaction completely. And then, of course, you get the 8. Well, when we add these two reactions together, we're going to get the 8 in front here, the 5 here, the 5 here, and the 4 here that we did in our last example. So, this is a reduction half reaction, oxidation half reaction. The two are added together to give you this net redox reaction. So let's practice another one. But now we have to balance in a base. Now here's a chemical reaction that you need to balance as a redox reaction, give a net reaction to, and then want to balance it in a base instead of having it swimming around in what we call acidic medium. How does this reaction occur in a base? Okay, now, this reaction is quite incomplete. You can see, like if I say oxygen and iodide ion react to form water and iodine. Okay, that's fine, but there's no hydrogens on this side here. We're missing elements. It's a beautiful key to be able to say, you know what, I need a half reaction method. I need to build my own half reactions. So quite simply, we start with, okay, we got O2 and H2O, I negative and I2. So let's make the I negative turn into I2. This turns into this. And then the O2, well, that's going to turn into the water, obviously. And even if you didn't even put water here, oxygen, we got it on this side. What do you do when you need to add oxygen? You add water. So we're going to add water to that side. Now, let's finish this reaction. 2 I's here, 2 here. And so if we've got 2 negatives on this side and 0 here, we know we need to add 2 electrons here. So what we've got is we've got oxidation occurring here, and that means that the I negative on this side is a reducing agent. Okay, now let's finish off this half reaction here. 2 O's here, so we've got to put a 2 there. Oh, that means we need 4 H positives on this side. It make sense? Now, we better need electrons on this side, because otherwise it won't work. Oh yeah, but look, 4 positives here, 0 charge here, so we need 4 electrons. So, when we add these two reactions together, we've got to make sure that we double up on this one because, remember, 2 times 2, 4 electrons lost must equal 4 electrons gained. Okay, and so the net reaction is going to be, when we do that, it's 4 I negatives plus 4 H positives plus O2 makes 2 H2Os plus I2. But how many I2s? 2 of them. And that's the reaction now balanced in acidic media. But we want to actually put it in a base. We want to balance it in a base. So here's the rules for balancing in a base. When you finish that reaction, just doing it the normal way that we did, add enough hydroxide to cancel out the H positive and turn it into water. Because you know H positive and OH negative make H2O. So here's what you do. You say, oh, okay, well, I've got 4 H positives here, so let me add, I just like to do it this way, add 4 OH negatives here to this. So I get 4 HOH, see, HOH, 4 of them. Oh, HOH is water, right? So now we've got 4 waters on this side, but whatever you do to this side, adding 4 hydroxides, you add 4 hydroxides to this side. Whatever you do to one side, do to the other side. Now listen. You may have to cancel down the waters. Watch. Because now we've got 4 waters here and 2 waters here. Remember, like terms on each side, got to get rid of them. So that eliminates the 2 waters here and eliminates 4 here and leaves us with 2. So now you can see that we've got 2 H2Os left here. And so we write down plus 2 H2Os plus O2. And then we get rid of that water there entirely because it canceled out. And so when we do that, there we go, we get that reaction as our net ionic equation when this reaction here is balanced in a base. So we've got a current of electrons that goes from the anode to the cathode. Well, if we know the current in terms of its amperage, or how many coulombs of charge is going over from anode to cathode per second, and we actually can measure the time, we can do some fancy calculating in terms of how many moles of electrons are going. And moles of electrons can tell us how much mass is deposited at a cathode or broken down at an anode. Oh, wow, that's cool stuff. Okay, but here's the formula you need in order to do that. The number of moles of electrons equals the current. And now it's kind of funny because I stands for current, but it's measured in amperes. That's current. But we don't write amperes in our calculation. We write coulombs per second, C over S. The time is always measured in seconds, so that cancels out and leaves us with coulombs. And F is Faraday's constant, in honor of Michael Faraday, who was one of the great scientists, period, of all time, back in the 19th century. F Faraday's constant is 9.65 times 10 to the 4 coulombs of charge every time you have 1 mole of electrons. And with that now, we can do some really cool calculations. To do this question, you got to get first that copper 2 sulfate, which is an ionic compound, and break it down to copper ions, sulfate ions, and water in solution. Now, when you look on your chart, you'll find that Cu2 positive is the strongest oxidizing agent. It's one of the equations here. Water is actually the reducing agent. But since the question is saying how much copper can we plate, I only care about the copper half reaction. So find the metal that you're looking for in these calculations and write the half reaction in the data booklet for that metal. Here's the half reaction for copper ions turning into solid copper. Now with that as the basis, take that number of moles of electrons that equals IT over F and plug in your current. Now notice that I wrote amps in here, but really that won't cancel with coulombs here unless you write coulombs per second. It's the best way to do it. Now you see, when you do this math, and look what I did. I took the 20 minutes and turned it into times 60 seconds over minutes. I didn't have to actually just worry about just putting in the seconds. I do all my conversions in the calculation itself. So coulombs is going to cancel coulombs here, and you're going to get seconds canceling seconds over here, and minutes here, and minutes here, and you're left with 1 over 1 over moles. And 1 over 1 over moles is moles. But that's moles of what? Number of moles of electrons. It's the moles of electrons here. But how do you get the moles of copper? It's a 2-to-1 ratio. So look, here's the moles of electrons from there. And now I cancel out the moles of electrons, leave myself with moles of copper. But we don't want moles of copper, so we put that on the bottom. In the next part of the ratio, we want grams of copper. That's the molar mass of copper. And then when you do this math, you get 0.79 grams of copper that can form in this reaction. All over Alberta, you'll see signs like this one, and some of them will actually have warning cathodically protected cable below. What does that mean? That means then that there's a metal pipe under the ground that they're running a current through to protect it from corrosion. That's cathodic protection. There's lots of different ways to do that too. How can you protect iron pipe under the ground or metals anywhere from this? This O2 and water half reaction, when oxygen and water are in the environment, they love to gain 4 electrons to turn into hydroxide. And they'll gain them from left over right, because this is the way they're arranged on the chart. They'll gain them from iron and take iron and break down iron. Or magnesium and break it down. These are valuable metals. And so we have to find a way to be able to prevent this reaction from causing so much damage. Well, how do we do that? Well, we can paint the surface of the metal. That'll keep this away. We can actually run an electrical current along a piece of iron. That'll supply the electrons to this instead of the iron. So we can protect the iron from this cathode, because it's undergoing reduction, through cathodic protection. But the neatest way in order to accomplish this is to take a piece of magnesium and just touch it on or wrap it around the iron. What the magnesium does is, because it's a stronger oxidizing agent, this is the arrangement of them on the chart, that magnesium will actually protect the iron and donate its electrons first. So will zinc. And therefore, that's why we coat nails with zinc. It's called galvanizing, because then it protects the iron, which does the major part of holding the fence together, and the zinc rusts first. Cathodic protection. That is so cool. Somebody comes up to you and says, hey, balance that reaction. You know, just right off the street. Balance that reaction. You say, well, okay, I think that's a redox reaction, so I'm going to balance this, and I'm going to make sure not only do I have to balance it atomically, but you have to actually worry about these charges too. That equation actually can be kind of tricky to balance if you don't have a technique called oxidation numbers to be able to solve it. Let me show you what these are all about. Oxidation numbers, or oxidation states, are numbers that we assign to various elements, kind of an informal type of charge that we give them, in order to determine whether or not they gain or lose electrons in chemical reactions. Now, I'm going to give you all the rules for oxidation numbers as we go ahead and just do them right now. So I've got a whole bunch of chemicals here listed on the board, and we'll just go through them and assign oxidation numbers. And then you'll be able to give oxidation numbers for everything. Here we go. All elements in their natural state, the way they're found in nature, they have oxidation numbers equal to 0. So, if you look at oxygen, oxygen in its natural state, O2, so we put down underneath oxygen a 0. That's its oxidation state. What about hydrogen, H2? 0, because that's the way the element is found in nature. All right, now, here's H positive. When hydrogen is not in its elemental state, it always has a +1 charge. Also, any type of free-floating ion has as its oxidation number whatever charge it is. And so therefore, because that's a +1, hydrogen is +1. And it's always +1 in a compound. Hydrogen is +1. Now, here is SO4 2 negative. And you've got to assign oxidation numbers to the sulfur and to the oxygen. Well, here's the rule for oxygen. When it's not in its elemental form, but in a compound or any kind of chemical, O is 2 negative. There's an exception, and there's a couple of them, but I'll tell you that in just a second. Just 99% of the time, O is 2 negative. So, or -2. So here's sulfur and oxygen, and we give oxygen a -2. We just write down what one oxygen is here, but there's 4 oxygens, so now get this. -2 times 4 is -8. But this polyatomic ion says, I only want to keep a 2 negative charge. So what does the sulfur's charge have to be? +6. Because +6 added to -2 times 4 equals a total of 2 negative. That's how you do oxidation numbers in polyatomic ions. Okay, now, hydrogen is always +1. But oxygen here can't be -2, because look at, -2 times 2 would be -4, plus 2 would give you a 2 negative charge, but this hydrogen peroxide is 0. So oxygen in hydrogen peroxide is -1. That's an exception. Oxygen is always 2 negative, -2, except when it's in hydrogen peroxide and see OF2? Fluorine is more electronegative on the periodic table. Electronegativity is something you learned in grade 10. And there's only one element more electronegative than oxygen, and it's fluorine. So fluorine gets its normal charge of -1, which means that in this case, the total must be 0 for this molecule. -1 times 2, that's a -2 total. Oxygen has to be +2 in order to make a 0 charge for that compound. No, there's a couple of exceptions for oxygen, but 99% of the time, oxygen is -2 in a compound. Like this one. Oxygen is -2. So what does that make each potassium here to give a total of 0 here? You with me? +1. +1 times 2 is going to be +2, and -2 makes a 0 charge. So what about this though? Look, there's no oxygen or hydrogen in the compound, so you don't know anything for sure. But when you see that, you break chemicals down into their ions. K is normally positive, and S is 2 negative on the periodic table. Those are their ionic charges. So when you're stuck, break things down into ions. And look, that +1, that goes there. That -2, that goes there. It goes -2 here. It's 2 negative here, but it goes -2 for an oxidation number. -2 plus 1 times 2 equals a total of 0. Ah, it's beautiful. Look at this one. Hydrogen is always +1. +1, that's 8. The total is 0. What is going to be the oxidation number of the carbon here? Oh my goodness, that's crazy. Look at that. It's going to have to be a negative, first of all, and it's going to have to be a fraction. But look, if you go -8/3, I know it sounds kooky, but look, -8 over 3 times 3 is -8. Yeah. Plus positive 8 gives you a charge of 0. You can have fractions as oxidation numbers. -8/3. Yeah, it's fine. This one is huge. But if you take the Na here, and this is actually a polyatomic ion, and break it down to its ions. Na is positive, Cr2O7 on the polyatomic ion chart, that's called dichromate, it's a 2 negative. Na positive plus 1. All of this has to equal 2 negative. Oxygen is always -2. -2 times 7. negative 14. What does each chromium have to be here? Plus 6. 6 times 2 is 12. Plus negative 14 equals 2 negative. And so you just take those, transfer them here, plus 1, plus 6, minus 2, and that's how you do oxidation numbers. And believe it or not, that's going to help in balancing that last equation. Watch. This equation can now be balanced successfully using oxidation numbers. So if you've got an equation and you're saying, how do I balance this thing? Use oxidation numbers. Watch this. It'll actually open up the whole world to you. Yeah. Oxygen is always minus 2. Minus 2 times 4 is negative 8. Got to keep a negative 1, so that makes the manganese plus 7. You with me? Hope so. H positive, plus 1. Fe2 positive, plus 2. Plus 3, plus 2. Oxygen's always minus 2. Hydrogen's always plus 1. That works out for water, giving a total charge of 0. Watch this. You notice that from one side to the other, oxygen stays the same and hydrogen stay the same. They don't undergo a change. They're not involved in this oxidation-reduction reaction. But the Mn goes from plus 7 all the way to plus 2. If you go from plus 7 to plus 2, you have to gain negatives to become less positive. You know what I'm saying? Plus 7 to plus 2, which means that you have actually gained 5 electrons. This Mn gains 5 electrons going from here to here. Oh, wow. Then that means gaining electrons, that's reduction. And reduction means that Mn in this compound is the oxidizing agent, which is undergoing reduction, which is gaining electrons. Oh, okay. What's the iron doing? It's going from plus 2 to plus 3. In order to become more positive, you have to lose negatives. And so that's a loss of 1 electron. Hey, if you lose 1 electron, what are you undergoing? That's oxidation. And oxidation is meaning that this is a reducing agent. Reducing agent, undergoing oxidation, losing an electron. Oh, baby. Now, look at this is a redox reaction. And now you got to pretend that you're adding 2 half reactions together. Look. If this wants to gain 5, but this only loses 1 at a time, what do you usually do when you have like a half reaction that has 5 in it and 1 electron in it? You multiply the one that has 1 by 5. So we take this, we multiply it by 5. But that means then that this is involved in this half reaction. So if that's a 5 there to get 5 electrons, you got to put a 5 here. You got to put a 5 here. We're balancing it now. And now we've got the proper amount of gained and lost electrons, 5 each. And what we have established is the initial point of the balancing. We don't actually have it fully balanced yet. Now we go from here and just go one element at a time. But oxidation numbers gives us the diving board, and we just could jump off into the pool now. So, 1 Mn, 1 Mn, 4 Os. Oh, 4 Os. 8 H's. 8 H's. 5 Fe's and 5 Fe's. And you're saying, well, we could have done that before. But you know what? It was the Fe's that messed everything up. But here's the thing. Look at the total charge. 1 negative and 8 positives. Well, what's that? That's 7 positives so far on this side, plus 10 positives. That's 17 positive charges on this side. Your equation has to balance in terms of charge on the other side too. Look, 5 times 3 is 15, plus 2 is 17. Baby, oxidation numbers can help you balance even the most difficult equations. What do we have here? This is a voltaic cell. It's named after Alessandro Volta, who started inventing these things around 1800. They're also called galvanic cells because of, what was his name? Luigi Galvani. He's one who's credited with discovering electricity. They're all Italians, aren't they? Chem guy's half Italian. So, what we've got here is this voltaic cell made of zinc and copper with a copper 2 nitrate solution in the beaker, and inside this porous cup is zinc nitrate. Sometimes you'll see voltaic cells set up, and I'll give you this in the diagram in a second, with 2 solutions separated but connected with something called a salt bridge or a U-tube. So when the zinc goes into the zinc nitrate, the copper and in the copper nitrate, and you've got a connection between the two made by the porous cup allowing movement of ions through the cup, you get, registered on the meter, a positive voltage, which means that there is a current flowing from the anode, the zinc, to the copper, which is the cathode. Now, which is which and how do you tell and what ions are flowing? Oh, that's coming right now. So if we can take two half reactions, one where an electron is being lost, or electrons are being lost and then gained, and we can then intercept the flow between the reducing agent, who's losing electrons, and the oxidizing agent, who's gaining them, that electron flow, or electricity, we can utilize for power to be able to use cameras to film chem guy or with batteries in them, or calculators. Battery power, portable electricity, portable power, absolutely vital. It was discovered about 130 years ago. Well, let's take this reaction here, written in what we call cell notation, and let's draw what the voltaic cell would look like. A voltaic cell is an electrochemical cell that will produce an electrical current. So this voltaic cell, or galvanic cell, right? This one is going to be made from dichromate ions and hydrogen ions, acidified dichromate, and the carbon here is very interesting, and it needs to be there, and I'll show you why as we do the diagram. And this reaction, which is actually the SOA because it's gaining electrons, is going to react with a piece of tin in a tin 2, let's say tin 2 nitrate solution. This solution might be potassium dichromate. This acid could be H2SO4 or HCl, something like that. So we've got this half reaction for this right here, and we can either build that half reaction, or we can just look on a data chart, on a reduction potentials chart, because it's probably there. It's a very popular reaction. And so is the tin one. And remember, the highest one on the left reacts with the lowest one on the right, and through this list of chemicals here, that's what we've written here. Now, this is going to be the half reaction that gains electrons. Now, gaining electrons is reduction. That means it's an oxidizing agent. But here's what it means in terms of drawing the cell or building the cell. This, because it's reduction, will be the reaction that occurs at the cathode, or in the half reaction, the half cell that has the cathode in it. And this is the half reaction that's going to occur at the anode. So anodes for oxidation, the two vowels go together. Cathodes for reduction, and the two consonants go together. Okay, now, when we put this together, we're going to get a total voltage of 1.37 volts on a voltmeter under standard conditions, and you have to actually take into account the fact that there's resistance in the wiring and in the apparatus you're using where you might not get the proper voltage register. So, remembering that all of this here describes what's happening in anode and cathode, let's put this together now in a diagram form. Did my best. A cell diagram sets up for you how the electrons move from the anode to the cathode. Now, if you were going to write a test and you had to draw a cell diagram of something, you'd probably get almost half marks for, you could totally mess it up and still get pretty good. If you just draw the cell, you draw a connection between the two. Now, you can use a porous cup, which actually permits ions to flow from one solution to another. That's important, that's coming. Or you can use something called a U-tube, and you may have seen that in a chemistry lab. It's just a piece of glassware that has a solution in it that has stoppered at either end, stoppered with cotton so ions can still flow through. And inverted, tipped into solutions to provide a connection between the two half cells. Very important to do, otherwise this just won't work. Okay, so we always write down anode and cathode. Doesn't matter, I always like to go from A to C here. Follow the alphabet. And electrons will always go from the anode, which is undergoing oxidation, to the cathode undergoing reduction. So I draw from this bar, electrons leaving and going to the cathode. There, that's an initial diagram with a voltmeter attached in the middle. Now, to put the chemicals in. In the half reactions we saw previously, the anode was the tin reaction, or the tin reaction, occurs at the anode. So what we would have as this piece of metal in solution is the tin. The tin is the anode. The anode is the electrode here, and so that is SN solid. Now what about the cathode? What is the solid there? Well, dichromate and hydrogen ion, those two guys, they don't have a solid there. So we actually put an inert carbon electrode. You don't have to use carbon, you can use platinum, but that's pretty expensive. And the inert carbon electrode is the one that allows the electrons to come down it, and a reaction will take place in solution with the chemicals that pick up the electrons from the rod. So the carbon is the cathode, the electrode in here. That's the carbon. Now, what was the solution in here? The SN2 positive is actually breaking down. Electrons are going through, and the SN2 positive is turning into SN, or the SN solid is turning into SN2 positive in solution. And this solution is already a solution of tin 2, and we'll say probably tin 2 nitrate. We always put a nitrate in there with a positive ion if at all possible. Now, here's what's happening over here. There's dichromate in this one. Remember Cr2O7, 2 negative. That's swimming around with 8H positive. Well, they go to the bar, gain those electrons from the half reaction, and turn into the products of their reaction, Cr3 positive and water. So the electrons go from the anode to the cathode. These guys pick up those electrons on this rod that are provided by the tin. Now, in order to complete the diagram, we need to complete an electrical circuit. We've got electrons flowing this way, but what's the purpose of connecting the solutions? We need migration of ions, and here's the ones that go. This is an anode. It's called an anode because it's the electrons that anions flow to. Anions migrate to the anode. And migrate means you come from the other side. And so what is an anion or a negative ion in this solution? Well, the dichromate is negative. It's also involved in the reaction. But remember, this H positive means that there's probably Cl negative swimming around. This Cr2O7, 2 negative probably meant that you used potassium dichromate to make this solution. So you've got a whole bunch of different ions in solution. The Cl negative, or the dichromate, is an anion, and they can go through the bridge. It's called a salt bridge. This U-tube is actually called a salt bridge because the chemical that you put into it could be a KNO3, something that is entirely soluble that won't precipitate. That's important. But you have to have a conducting solution, it has to be ionic solution, to let ions be able to be conducted and flow through. Hey, okay, so you've got anions that migrate to the anode. Those are charged particles that are migrating, but at the same time, cations in here, like SN2 positive, migrate to the cathode. Anions migrate to the anode. The cations migrate to the cathode. Okay, so the thing is, you've got a migration of ions and current of electricity moving, and that actually completes the electrical circuit. We can take that flow of electrons now, intercept it. We don't have to put a voltmeter there. We could hook that up to a Walkman or something like that. But you look kind of silly with this wet cell, not a dry cell, hanging around your neck powering your Walkman. Cell. Plus, an electrolytic cell is non-spontaneous. We're putting electricity into that cell to create a chemical reaction. Voltaic cells take chemical potential energy and convert it to electricity. Electrolytic cells take electricity and convert it to chemical energy. So that's the difference between those two cells. And one has, the electrolytic cell has a negative E0. The voltaic, of course, produces electricity, so it's a positive E0 value. Okay, so if somebody said we take a nickel 2 chloride solution, which is nickel ions, chloride ions, and water swimming around, and we zap that solution with a power supply. Each one of those is a cell of a battery or power supply connected in series, so we add the voltages together. And electrons always go from anode to cathode. Now what would we use for the electrodes here? Platinum or carbon. Inert electrodes are best. Dip them into solution, zap that solution, And you can get nickel ions turning into nickel and water turning into oxygen and hydrogen ions. So you would see bubbles at this is oxidation, so it occurs at the anode, so there'd be bubbles coming off the anode and nickel forming on the cathode. Now, an electrolytic cell, again, has a negative E0 voltage and means non-spontaneous, so we have to add electricity in. There are some cells, too, that actually produce electricity and bring it back in and are rechargeable. And those types of cells are electrolytic and voltaic, like this one.
Okay, car battery. It's called a lead storage battery. It's got lead plates inside of it, which makes it really heavy, and lead-4 oxide plates as well. And then intermingled between those plates, you got sulfuric acid as the electrolyte. These batteries right here are not only voltaic, as they actually produce an electrical current to start the car, but they're electrolytic as well, because they're being recharged. And as the car is running right now, see, you got your motor over here, and then it's creating a lot of energy, which is traveling through the dooflinker here, and then you got your goosemitch down there. Now the goosemitch is going to be able to send a lot of stuff to the whatchamacallit, and then that feeds electricity into the battery. And so what we've got again is a circuit, and we've got, oh, and by the way, this is very important. There are 6 compartments inside of a lead storage battery, all hooked up in series. Get that, in series,